going to get started. So today we're going to talk about,
real close.
okay. Today we're going to talk topological data analysis. And we're very fortunate to have Anthony Bak here from
AYASDI.
to take us through it. And Anthony is the principal scientist at AYASDI, and previously he was a postdoc at Stanford where he and his advisor worked on some really cool stuff that became AYASDI. So let's please welcome Anthony.
Thank you for, I'm not sure this is going to work. I think I'm going to just try and speak loud. That might be easier than being tied to the mic. All right, so I'd like to tell you about topological data analysis. So what am I going to do? First, I'm going to talk a little bit about the data problem. This is something that most of you are familiar with, but I want to reframe it slightly for you. Then I'm going to talk about how we solve this problem. And we solve it with topological summaries. And I'm going to go into some detail on what these summaries are, how they're created, what they tell you about your data, and look at some examples, some simple examples, just so that you get a feeling for the differences between the topological methods and other methods you might be familiar with. And then I'm going to come back a little bit and look at why topology. Most of you probably didn't study topology if you studied data analysis, so I want to come back and look a little bit about why, if you thought about it, if you knew about topology, why you might think it's a good tool for data analysis. And then I'm going to end, I have, in the deck here, I have sort of just a whole string of use cases, probably far more than I can possibly cover, but I'll just go through some of them and then until time is up, more or less, and show you what it looks like in practice on real data, mostly data from actual customers. Okay, so one caveat is that I'm talking about the kind of topological data analysis done by AYASDI. There are other kinds out there. There are other flavors. There are other tools and techniques. For instance, if you know about persistence or persistent homology, that's not really going to come up at all in this talk, but it's a fascinating talk for another time. All right, so the data problem, as I like to think about it, is how to extract meaning from complex data. So I don't really want to necessarily think in terms of big data. So big data is just one way that data is complex. Another way is with very rich features. And I'm thinking of genetic data, where when you look at gene expression levels, you typically don't have, say, tens of thousands or millions of individuals. You might have 100 or 200 in the study, and yet you have thousands or hundreds of thousands of coordinates describing those individuals. So the data is not complex because it's sort of, just huge numbers of points. But it's interesting. It's interesting because it has to do with our health and survival, etc. So I really want to think about complexity, not just bigness. So what is the problem with complexity? The way I like to think about it is that there isn't a single thing happening in the data. If you go back again to the gene expression example, and you're studying, say, cancer, the gene expression information doesn't just contain information about cancer. It contains information about normal cellular function, cellular reproduction. It contains information about all kinds of things that are unrelated to the thing that you're interested in. So this is the multiple story happening in your data. Another way of thinking about that is maybe you walk into a room full of people and all you hear is white noise, right? That's a problem of too many stories happening at once. And what you want are tools to summarize the conversations or to zoom in on a particular conversation. And that's the kind of thing we're going to do with topological data analysis. Another problem with big data is that there are too many hypotheses to check. There are too many different things that can be going on, and you can't check them all in a systematic way. So what we need is a way to generate hypotheses from our data problem so that we know what the right questions to ask are. Or another way of thinking about that is that what we want are answers, and then we'll figure out the questions later. So I'm going to talk to you a little bit, sort of, that's a philosophical statement, but this is really a math talk. It's a technical talk. So I'm going to describe to you what that means. What does it mean to get an answer first, and then try and figure out the question? Okay, so TDA, topological data analysis, is the tool that summarizes out the irrelevant stories to get at something interesting. That's what I'm trying to describe to you. And the shape, or the segmentations, the groupings, the cycles, represent verified hypotheses, but you have to figure out what they're telling you. Okay, so let's back up a little bit. That's more or less the goal of what I'm trying to tell you, is that slide. That's why I'm trying to convince you that we have a method to do what's on that slide. But let's step back for a second and look at, what do I mean by shape? Because I said the whole tool rests on summarizing shape. Well, shape is something we're all actually familiar with, anyone who deals with data, right? This collection of points, right, it forms a line. That's a kind of shape. It's a very simple shape, but it's also very useful. Linear regression, we fit a line, and now we can use it to do prediction, right? It's a simple shape, but it's one we're all familiar with. Here's another shape. It's clusters. Well, maybe you say, how is a cluster a shape? Well, asking how many pieces something breaks into is essentially the most primitive question about shape. And I mean that in the sense that mathematicians consider that the most primitive question. How many connected components? So there's another kind of shape we're familiar with, clustering. So here's something that begins to look like maybe what you think of when someone says shape. It's a circle. Well, what do circles typically represent? Well, not always, but a lot of times they represent periodic behavior in your data. So the shape, having a circle, says that there's some one parameter family of periodicity in the data, which you can go and find. So here's my final simple shape. And I want to think of this as being a collection of flares. And the way I'm thinking about this is a taxonomy of something that's happening in the data. It's weaker in some sense than clustering. But the way you should think of a flare is that as you move out in the flare, right, some property of the data is becoming more extreme. Maybe you want to think of one of these flares as being a normal person, and then you have two kinds of diabetes. And how bad your condition is with diabetes would represent how far along that flare you are. So it's not that you have it or you don't, but there's a kind of degree of having something. And that's represented in flares. So these are sort of simple shapes that we're all familiar with. And I'll point out, though, that our tools for discovering them are very different. Right? We have linear regression. We have Fourier series for the circle, right? There's a whole kind of industry built around understanding spectrum and understanding periodicity. We have clustering, and then we have, I'm not exactly sure what you'd want to call that, flare something. But the point is that these are all, the shape here reflects fundamental things going on in the data, and there are a whole industry built around each one of them, detecting them. What we want to do instead is step back from this problem and say, what's a way to, without judging what the shape should be, detect what it is? So that's what I mean by geometric summary. We want a tool that will figure out what the shape is and tell me, without having to know, do I have periodic behavior? Do I see linear regression? Is this a clustering problem? Should I be looking at the flares? Right? Without having to go and check each specialized tool set independently. So, just to give some more details on shape. So, one way, a quick way to describe shape is that shape is the global realization of local constraints. So, an example, if you're familiar, would be manifolds. So in this situation, a manifold is something that's kind of smooth, that locally, if you zoom in enough, looks like Euclidean space. Manifolds, for a manifold, the constraints are uniform and smooth over the surface. And I'll point out that this is too restrictive. So I really want to get this sort of out there because I feel like people talk, about the manifold hypothesis, or are there manifolds, can we detect manifolds? And we just don't see a lot of manifolds in actual data problems. So you don't want to build your techniques of discovering shapes around this very restrictive class of shapes. So in particular, we want to detect things that are sort of blobs and flares, and where the constraints on the data change rapidly as you move through the space. So your local dimension isn't really even a well-defined property. This is what data looks like when we look at it in most situations. I should say outside of physics. In physics, data does look like a manifold because the equations are extremely uniform. Or maybe I should say because there are equations, because there are nice algebraic equations you can write down. But outside of that, sort of in the data we're talking about today, when I say data, I mean like data from social networks or businesses or text analysis or whatever. This kind of data doesn't look like a manifold. So that's why we're using topology instead of geometry. We want to do this analysis of shape and understand what shape looks like while using as few assumptions as possible. We don't want rigid assumptions. And why do we do that? Well, what's the benefit? We reduce bias, we get more robust results, and the tools are very flexible in how and where we can apply them. Okay, so now I'm going to describe to you, that was kind of the philosophy section of the talk, and now I want to describe to you what it is that we actually do. All right. Thank you. I was getting worried, actually, about my throat. Okay, so I want to start in what I'm going to call math world. So I just ranted about manifolds, and what I'm going to do is draw a smooth manifold. Despite the fact that I just told you data never looks like a smooth manifold, and that's because I want to draw a nice picture for you. And I'm going to use the word function, and the functions that I draw, they're going to look like smooth or continuous functions, but this is not an assumption that we need. So when you, going forward, so when you actually want to apply this, smoothness and continuity are not really things you have to worry about. And I think I beat these 2 points already, that we really don't want to consider manifolds. Nevertheless, here we are. Here's my data. So when I'm drawing the data this way, in this math world way, I'm thinking of it as being the surface of a smooth manifold, or if you want, being very densely sampled on a smooth manifold. So this is a pair of pants. The inside is hollow, there's a trunk, and there's 2 legs. And I'm drawing it out for you, and something just really to remember and to keep in mind is that you never get to actually see your data, right? Complex data, by definition, it's too high dimensional. You never get to actually visualize it, but I'm showing it to you because I'm going to show you what a summary is, right? That was the goal. That's what I said I'd be doing, is creating data summaries. And in order for you to understand, well, what have I summarized, I need to show the original thing as well, so you understand what it means to summarize a shape.
Yeah, one question.
Yeah.
Does the envelope of the data, there are data points residing in this envelope?
Yeah, so you're thinking of the data points as living on the surface of these pants. But actually the way I'm going to draw it, and the way I'm going to talk about it at the beginning here, I'm actually thinking of the surface as a continuous surface. So I'm not sampling at all. This is a kind of idealized world. And we'll get to the sampling and how you handle that in a moment. Okay, so how do we start? So the input into the system is the data, and implicitly here there's a metric on the data, and the metric is what I've drawn out. Now I have a function, f, so I'm going to summarize. So to summarize the data, I need to know what to remember and what to forget. And the function is the thing that's going to tell me what to remember and what I forget. So I'm going to summarize with respect to a function, and I've just drawn that here as a height function. meaning every point on those pair of pants goes sort of just straight across to some value on this line. It's a real valued function. So to summarize the data, I take a point P in the range of the function. I look at the inverse image set of P, and for every connected component, in my summary, I'm going to draw a dot. Okay? So that's it. That's the procedure. This is now going to make a summary. If I look up at this point Q, right, I take Q, I take the inverse image. Now there are two pieces in the inverse image. So when I go over to my summary, I'm going to draw two dots. And now I just repeat this procedure for all the values of the function f. When I do that, I get a y. So what have I summarized? Well, I forgot the hole in the pair of pants, right? But I've remembered that there's a trunk and there's two legs, right? So this is a summary of the data. It's a reduction of the information content in the data. Now I'm going to go, I think this is maybe more useful if I describe another function so you can see what a different summary would look like. This is just one summary. So I'm going to take this function g, which sends points kind of just down to this line, and do the exact same procedure. I start with a point p prime on the edge. I look at the inverse image. It's that whole sort of hem or seam of the pair of pants. There's one piece. I draw a point. Moving in slightly, I have two pieces. I have a front piece and a back piece. So down in the summary, you'll see two dots. I drew two dots. Now I'm just going to keep going. As I go around, this is going to connect back up, so I get a circle. In the middle, there's just one piece again. I can loop over the top of the saddle. So there's one piece, and then symmetry on the other side, I have a circle again. So this is a different summary of the pants. I get a pair of eyeglasses, and I forgot now that there's a trunk with two legs, but I've remembered that there are two holes in the pair of pants. The legs each have a hole. So this is the method that we want to apply to data problems. We create we create summaries of the geometry of the data, or the topology of the data. In one case, we get the eyeglasses. In the other case, we get a Y. Okay, so why do this? What can you read off of summaries? So probably the most common way that we're going to apply this is that there's something else that we're interested in. We're interested in finding localization of something. So what do I mean by localization? I mean, this is my data, and here's a collection of data points that I'm interested in. Maybe these are the people committing fraud, or these are people with cancer, or these are people who have, who click through on my ads at really high rates. Right? There's some subset, some part of the data that is that represents the individuals I'm interested in. Well, what happens in the summary? They end up in if they're in this kind of small, compact region of the space, they end up in a small region of the summary, and I've learned something now about where those points of interest are. I haven't nailed it down exactly, right? But I've learned they're on one of the legs, sort of, 2/3 of the way out of the pair of pants. Well, we should be a little bit careful here. If I was also interested in this blue group, this summary F, they end up right on top of each other, the red and the blue. They end up in the purple region. So I don't get complete fidelity. It's a summary. It forgot those separating points. That was what was summarized out. Luckily, I have other ways of creating summaries. I have other functions that I can summarize with respect to. And in this case, you can see that I separate them out well on the bottom. And in fact, I would say that for these 2 points here, this function f that sort of cuts across is really the only function that's, or is really a special function in the sense that almost any other function I chose would have created a summary that separated out these 2 points. And this is what I would call an easy problem. Easy problems are where the points you're interested in are located in some small or some compact region of your space, And in those cases, summaries with respect to sort of almost any summary is going to, almost any function is going to produce a summary that's going to answer your question. And so there are some other methods, there are other sort of traditional methods to attack those kind of problems. When this gets interesting is when the quantity of interest itself has substructure, itself has geometric structure. So I'm illustrating that here by just kind of stretching out the points that I'm interested in. When that happens, you'll notice we have problems with our summaries. This function f now, I've kind of, the points of interest end up sort of almost everywhere in the summary. Right? This is a hard problem because the points themselves have lots of structure. Well, with G, I get lucky again and I can still summarize it. So these functions, they're also called lenses, inform us in the space, a way to look in the space for phenomena. For easy problems, many different functions are going to be informative. For hard problems, we have to be a lot more careful. But even then, you know, when we found out that green was smeared out, we actually did get some incremental knowledge. We were able to eliminate a whole leg of the pair of pants. So even in bad cases, we get incremental knowledge, and we just have to consider more functions before we truly understand how the points we're interested in are localized. Okay, so that's it really. That's sort of the story. It's sort of surprisingly simple in a lot of ways, but I would encourage you not to be, don't be fooled by the simplicity of the picture. Simplicity is a virtue that sometimes we forget about, that simplicity is really what we're after. Okay, I need to now show you, maybe I should explain my simplicity comment a little bit more. So it's like this. You know, what I've just done here for you is let me take an analogy with calculus for a moment. Right? If I'm trying to explain the derivative to you, I take a function, I draw it, and then I draw in the tangent line, and I say, look, there's the derivative. And you say, wow, that was easy. Like, what's the point of that? Right? And yet, sort of all of modern physics comes out of understanding derivatives and integrals, right? There's a lot of, it's very descriptive of the natural world. And in that sense, I would argue that these summaries are very descriptive of the data world. Now, of course, you have good reason to be skeptical of that comment, and that's fine. I mean, you haven't learned TDA, and you haven't been thinking about it, and, you know, I'm a little bit of a zealot, so, you know, we'll understand there's a disconnect, and well, that's fine. I hope to convince you to at least consider this simple picture a little bit more. All right, so now I want to move into the data world where we're going to get rid of this kind of sheet, this manifold thing. I'm going to show you how to build a summary in a, where we have data points instead of a sheet. So what I do is I replace points in the image with a range. So with an open set in the image of the function, and I'm going to replace connected components of the inverse image with clusters in the inverse image. And then I'm going to take these clusters and I'm going to connect them with an edge if they share points in common. Right? So in the continuous case, when I could just say, now you do that procedure from top to bottom and you draw what you get. In this kind of disconnected data case, I have to tell you how to connect stuff up, and you connect it this way. If clusters share, you connect two clusters with an edge if they share points in common. Okay, so what does that look like? So here's our idealized world. Now I'm thinking of it instead as being kind of sampled by points, the space. So I take, instead of a point, I take an open set in the range of the function f. I look at the inverse image. This is part of the cylinder below that dotted line. I do clustering. I find two clusters. So I've drawn two dots over on the right for my two clusters. Now I go up a little bit, but I go up in such a way that these sets are overlapping. Now I'm on this middle band here. I do clustering again. I find I have two clusters. But there are these points in the middle here that are in both U1 and U2. Right? There's this middle belt there. So when I did clustering in U1, they went to one node. And when I went to clustering in U2, they went to another. that gives me an edge to connect up those two clusters. So I get something like this. And now I just continue on, and I do that covering the range with clusters, and I get something that looks like this. So again, it's remembered the Y aspect of that pair of pants, right? It's summarized that there's this Y shape. It forgot that there's a hole. But it has these, connected clusters. There's more structure in the graph because of the clustering. So that's it. That's the method. That's what we do with data. Okay, so there are some subtleties here. I keep saying, I keep saying function, and the text up here says lenses, right? I'm summarizing with respect to these functions. Where do these functions come from? How do we find good functions? Good functions will create good summaries. Well, luckily, this is not a problem we actually have to solve, because people have been finding functions on data sets sort of for as long as people have been studying data. So some examples would be statistics. Any kind of summary statistic of, say, a row in a data table is a number assigned to that point in the data set. That's what a function is. For every point, I give you a number. So statisticians have been coming up with functions on data sets for a long time. Sensible functions. We also have functions that come from geometry. So we can take centrality, or we can measure how far a data point is from the center of mass. We can look at curvature if we have a very finely sampled space. We can look at, for harmonic cycles, this is a way to automatically detect loops in your data set. Machine learning also sort of has been coming up with lots of functions on the data. So PCA, SVD. In that case, I'm using the coordinate of a PCA as a function. So PCA1 gives me a coordinate. It gives me, the X value for every data set, every point in the data set. If you want, you can use autoencoders to create functions. Sort of more modern versions of PCA, like Isomap, MDS, TISNI. These are all functions on the data set. You could also do things like distance from a hyperplane. You can look at error or debugging information for your machine learning model, etc. And then there are also data-driven functions where the function comes from the application that you're studying. Like maybe you're studying patients and you want to look at age, or you want to look at the date of something. So functions are kind of all around us already. We don't have to work hard to find them. Okay, so let me go a little bit more carefully into some examples. Yes, you have a question?
Are these functions hyperplenes?
So the function creates a summary. All summaries are sort of valid reflections of the data, right? So
we can do prediction on summary also.
you can do prediction of.
On summary, so it becomes hyperplenes.
Sorry, I can't. I'm not understanding your question.
Summary is also a hyperplenes.
A summary is a hypothesis. I'm not sure I understand that, but we can talk afterwards. Okay? So let me show how this works in some examples. Okay, so let's look in more detail at PCA, and I want to look at PCA because it's something that I think everyone is familiar with. So what do I mean to use PCA as a function into the TDA framework? So what is PCA? It's orthogonal projection onto the plane that best contains the data onto some plane of some dimension. It's unsupervised dimensionality reduction. It's easy to interpret. Finds the best linear subspace that captures the variance or spread of your data. And here's an example of it. So I have a data set. I took the first two PCA coordinates and I captured 98.4% of the variance. So I'm sort of tempted at this point, just looking at this, to think, all right, I have more or less 3 clusters in my data. I'm done. I've captured a good chunk of the variance. I feel pretty confident that I have 3 clusters. What I'm going to do now is use the x-coordinate as a lens, okay, or as a function. I'm going to use the x and the y coordinates as functions. So what does it mean to use 2 at the same time? It means I'm going to cover I covered the interval by little open sets. So here I'm going to cover the plane by open squares. They're going to be overlapping open squares. I'm going to look at the inverse image of an open square. I'm going to do clustering in the inverse image. And then as I move around to do that for all the squares, I'm going to connect up clusters that share data points in common. Same story that we already described. So what do I expect to see when I do this? Well, I expect to see, right, if I slice this up and I slice that up, I expect to see a bunch of clusters, sort of tightly connected nodes for each of these clusters here, right? Since I've sliced the data, I'm not going to get one cluster for each of the clusters I see, but I'll get many clusters, but they'll be tightly connected because the density of points is going to make sure there's lots of points in those overlaps, so there'll be lots of edges. And then in between the clusters, I expect the edges to get more sparse because there's fewer points there in the overlap to make edges. So here I'm going to show you what happens when I do that. So this here is what it looks like in the software. Well, I found a surprise, which is that there are 4 clusters, not 3 clusters. So the question is, well, did I make a mistake with the topology? Or did PCA miss something? Well, in this example, PCA missed something because I cooked it up to illustrate this point exactly that PCA misses things. What did it miss is that I hid a cluster in the direction perpendicular to the projection direction. Like PCA is just linear projection. So I can place a cluster, right? I can slide one on top of each other, and then when you look at the projection, they get piled on top of each other. Why did we not get fooled by that? Because we always go back to the original space to do the clustering, right? So if there's a gap there, if there's a metric gap, we're going to see that, and we saw that in this case, that there were 4 clusters instead of 3. Well, you might say, well, you could have just taken another PCA direction, and then you would have seen that extra cluster. Well, the thing is that no matter how much of the variance you capture with PCA, as long as it's below 100%, I can hide arbitrarily complex geometry in that little gap. So no matter how good you think the method is, you can hide what may be the most salient feature in that small statistical gap. But we work in the system, the topological system will not miss that. So there are 2 essential problems with PCA. There's the one I described here, which is clusters get compressed on top of each other. There's another problem which is similar, I'm not going to go into details, which is that you get a phantom cluster because the fiber of the PCA map is large and the points can be spread out very far from each other in the fiber, but they all get compressed down by the projection. Okay, so PCA, we like it, it's easy to interpret, unsupervised, blah, blah, blah. The problems, clusters are distinct but projected on top of each other, points falsely clustered because of projection, and we always cluster in the inverse image so we don't see this problem. This here is a little bit of a general theme, which is that you can layer the topology on whatever your favorite analytics methods are, and will extract information that you've been overlooking. So whenever you have a function on your data, there's topological information, right? There's a topological summary that function captures. And you can choose, and what you can do is you can just, so TDA is the system that extracts that overlooked information, right? It just adds more fidelity to the things that you like already. So that's a sort of meta theme here. So I'm also going to now look at Isomap. So Isomap is based on geodesic distances instead of on the embedded distances. And it's nice because it can find low-dimensional manifold structure or visualizes maybe low-dimensional manifold structure in high-dimensional spaces. So if you like manifold learning, you can kind of still do that. So this is an example of using Isomap as a lens, and it's one of the few cases that I've seen manifold structure come out of our software. And the reason is that this here is actually a physics or a chemistry problem, and it's about how the conformation space of a certain molecule cyclooctane. So the molecule, right, can bend. So in some configuration space, a point in the space corresponds to the molecule being in a certain conformation. You can write down what that means. You can actually write down equations to describe what this conformation space is. It's an algebraic variety. Unfortunately, you can't figure out what that variety is. Right? So this comes from some research problem I worked on briefly. And but what you can do is you can get a triangulation on it using the topology. Now, what's the advantage? There are lots of ways of triangulating manifolds. What's the advantage of the topology? Well, if you go back to the beginning, one of the things I said is that we want as few assumptions as possible. You don't have to know that this is a manifold to get something that looks like a triangulation of a manifold out. And in fact, with this particular problem, in order to do the triangulation, there's actually, what you see here is a sphere with a Klein bubble glued on the inside. And that gluing creates a singularity. And the normal sort of manifold techniques were failing because they didn't know that there was a singularity. Someone had to model the local form of the singularity into how they did the manifold reconstruction. When they did that, they were able to get the right reconstruction of the manifold, right? So they had to work really hard. They had to know very specific things about local structures of singularities. And I stuck it in this here. In this case, I'm using it in the system. I don't have to know any of that. I don't have to have any assumptions about what it's going to look like, but I get a legitimate summary out at the end. And that's what you want. You want to really, when you're doing data analysis, you want to have to know as little as possible. Why? Because you'll never know everything anyway. Right? Of course, you always have an advantage by knowing more. But you want your techniques to rely on knowing as little as possible to still be valid. And that's one of the advantages of topology. Okay, so here's another example of using these summaries to look inside of a machine learning model. And in this case, this is done in a black box fashion, meaning I don't know what the model is. And also, I'm going to be a little bit vague about what we're looking at because it's someone's actual data that I, have pledged not to reveal. So the data is customer attributes, usage information, and contractual information. The problem is that customers commit fraud. Fraud is reflected in them being more expensive for this company. So what they did, so this is what they did, this isn't what I did. They created a kind of ensemble of different models that would flag people for fraud, and then they would use the ensemble to identify the actual customers who were fraudulent. So I'm going to make a data set that doesn't include any of the cost information, and that's important. I'm characterizing the customers purely by their behaviors, not by their costs, right? So I'm looking for, right, the fraud is in the behavior, the cost is just a consequence of the behavior. So I'm only using the behaviors to build the network. And now I'm going to look at who's being flagged by this ensemble. Okay, so this is now what sort of data more typically looks like. You can see, so this here are collections of nodes, right? These are like, these kind of blobs here, maybe you can't see in the resolution, represent very tightly connected clusters of nodes. And then there are sort of these more sparse regions in between these tighter collections of nodes. So collections of nodes represent sort of groups of customers that are more similar to each other. And then the sparse areas, if you're in a sparse area, you're kind of a more unique kind of customer. Right now what we're doing is we've colored by customer cost, and so you can see that there are, this group of customers. Remember, this is the group by behavior, more or less. These are high. I should say that the data space, the dimension of the space is 40,000. So there's 40,000 variables describing each customer, and there's. So I did this analysis, but I'm like totally blanking. I want to say there's like 30,000 customers, but then I'm not sure. There's definitely like 40,000 variables though. And what you can see here, so these represent groups of customers that are similar, that are high cost. Here's a very kind of nearby group that's low cost. There's some higher cost groups there next to low cost ones. Right? We get a kind of overview, a summary of the cost structure in our customers. Now, remember, high cost doesn't mean fraudulent, right? Because maybe there's legitimate reasons why you're high cost. And what we're looking at is these outlier models. So we're going to now look at the customers who are being flagged. So what you see is that across, so I'm just now counting essentially the number of flags, the times a customer is flagged, and coloring by the percentage. So a node represents a group of customers. I color by the percentage of the customers in that node who have been flagged. This is a mouthful. You got to really track carefully. The point is red is 100% flagged, right? And as you go down to blue, you get no flagged. Well, here, these are the customers to look at. We have the high, expensive customers and cheap customers, and then we have the flags, right? Kind of switching between the two. So here's something that they had no idea was going on in their data. They were considering each of their outlier models as being kind of an independent judge of who is fraudulent. And yet we see this consistent behavior that there's one group of customers that's always being flagged. Right? So maybe you might say, well, that's fine. Maybe those people are just the fraudsters, right? Well, what actually turns out to be is that there's an implicit bias in how they built all of their models. And their judgment of the models weren't independent. They all had a bias, and they had a bias for this group. But it was a bias that the people who were building the models didn't know about, right? They didn't know about it. But we were able to very quickly tell them, hey, there's this weird thing in your models where there's just this one group that you're flagging. Now, remember, this is 40,000 dimensions. There's fewer customers than there are dimensions, so you might be worried about the group, finding the group, right? How do you know well, there's all kinds of issues with that problem. Nevertheless, we get a very clear signal in the summary about what's happening. Okay. So the determination here was that there was a systematic bias. So this is where the summary and the topology, without explicitly asking the data, it told us where to go look. It said, look at that group. I didn't have to hypothesize that there's a group or that there's a bias or figure out how to do that, find that a cluster, a biased cluster. I knew afterwards, hey, I have to ask some questions about what's going on here and figure it out. And the answer turns out to be bias. So it tells us where to look in our data for problems and questions. Okay, so those were my kind of simple examples. And I'll come back to more examples at the end when I'll go through a bunch of use cases. But I want to take a kind of a step back for a moment and look at the why topology question. Why would you expect topology to be good for data analysis? So topology has three properties: coordinate invariance, deformation invariance, and compressed representation. And these are the properties that we're really using when we create these summaries. So I'm going to go through them one by one and show you why that's important for data analysis. Okay, coordinate invariance. So a topologist would say that the topology of a shape doesn't depend on the coordinates used to describe it. So this is actually one of sort of the different philosophical ways that we approach data problems. You can think of so many different feature sets can describe the same phenomena. So here's a very so why is this different than traditional methods? So I would say that if you look at statistics, so statistics is about studying, for the most part, a particular coordinate system used to describe the data. If I do statistics on, say, columnar information, columns of data, and then I just take that data and I rotate it a little bit, for the most part, my statistics of those columns are going to change completely. Right? They depend on the particular coordinate system I've used to describe the data. What we do is take a little bit of a different perspective, and we try and find those things out in your data that don't depend on the coordinate system you've used to describe it. So this here is the mathematician's viewpoint of how to study geometry. You don't study specific coordinate systems. The only thing that ever matters are the things that don't depend on the coordinate system. Right? Water boils where it boils. If I tell you it's Fahrenheit or Celsius or Kelvin, those are coordinate systems used to describe temperature. But those don't affect the phenomena of how water boils where it boils. Right? Coordinate systems are never the important thing. So rather than studying the coordinate system, we try and find out those things that don't depend on the coordinate system. So, and I'll point out too that frequently we'll change coordinate systems, scales, rotations, whitening, etc. When you do that, you're always looking for those things that are invariant under those changes. This is just restating coordinate invariance, right? If your result, if whitening created your result, then your result isn't real. The reason why you do these things is a limitation of your tools, right? It's a limitation of the tool set. It's not something intrinsic about data. That's not why you do these things. Okay, so here's an example. We're looking at a biological phenomena, in this case, breast cancer, and we want to compare studies of breast cancer. So, unfortunately, these studies are from different patient populations, and they measure different genes in the patients, and they're done with different underlying technology. And yet, I want to compare these groups of patients. So, what I would say is that there's one phenomena that we're studying, cancer, breast cancer in this case, but we have different coordinate systems on this phenomena. Different machines, different populations, different genes. So here are two summaries. One is from a Netherlands Cancer Institute study, and the other one is from another study. And this here is colored by a certain gene that's linked with cancer. And you can see we get this Y shape, right? The shape of the data was the same, even though all these other things were different about it. The summary was the same. So you can see there's a red and a blue flare in each. Those are the sort of abnormal populations we're studying, and then we have kind of the trunk is more mixed levels. And we see those same summaries, even with varying all this information that we're studying about cancer. So that's coordinate invariance, right? It's powerful. It allows us to be a little bit sloppy, right? We don't have to care as much about our coordinate systems. Deformation invariance. Okay, so topological features don't change when you stretch or distort your data, as long as you don't tear. So the advantage here is that it's going to make problems easier. It's going to make them noise resistant, less preprocessing of data. more robust table answers. So here's an example. This is a simple example again. So I have a line on the left. This is a nice clean line, and I have a noisy line on the right where there's a bunch of Gaussian noise added. Okay, so I'm going to use the x-axis as the lens, and I'm going to see what my topological summary is. Oh boy. So that line turned out not to be a line at all. It turned out to be a circle that was stretched out really thin. Right? So this is deformation invariance. I had deformed the circle so that it started to look like a line, and the noisy line was a noisy line, and look, I mean, lucky for us, we don't find structure in the noise, right? The noisy line looks like a line. The thing that looked like the nice line was actually a circle, right? This is sort of part of the idea, right? This deformation invariance goes back to bias. I could have tried to model it as a line, but that would have been my bias about not having looked carefully enough, right? If I had zoomed in on that line, I would have seen that it was a circle, but you know, it looked good enough, right? The correlation between these variables is 0.99999 out to 6 decimal places. I don't think to look for a circle in something like that, right? It really looks like these variables are essentially identical. And yet maybe this answers my whole problem. The top of the circle is one thing, and the bottom of the circle are, you know, all my fraudsters or whatever, right? We want techniques that protect us from our bias. Even the things that look like they're self-evident, like, gee, that looks like a line. Okay, so we can be surprised even when we think the solution is obvious. Both examples have near perfect correlation. Now, we could have transformed the data to try and look for that structure of the circle, right? But the point is, we didn't have to think of doing that. So when I talk about the robust answers, it's not that you couldn't have thought of some other way to get that same answer. It's that you never had to think of doing another way to get that same answer. That's what it means to be unbiased. That's what it means to be robust. You never have to think of that other way. Okay, so here's another one, 2 intertwined spirals. Again, I'm going to use the x-axis as a lens. And what do I get? I get 2 lines, right? The embedding, that's the deforming of these 2 lines, that they're embedded in this complicated way. But I'm finding those things, right? The point is to find the things that don't depend on these kind of deformations, right? I find that there are 2 lines. Okay, so I forgot something about the embedding. I forgot that the spirals were intertwined, right? So there is a forgetting process here. But the essentialness of that data set, right? The important, most salient features are that there were 2 lines. And I was able to find them here. Okay, so it was easy, take connected components of the graph. We take more information than clustering. Okay. All right, so the final one, compressed representation. And in some ways, this is the idea that is really driving what's going on here. So what's compressed representation about? Well, if you look at what we're doing, this procedure replaces a finite metric space, right? So no matter how big your data problem is, it's always finite. We replace a finite metric space with a combinatorial object. So this is where there's a point of confusion a lot of people have. You know, they say, well, is this just dimensionality reduction? And that question is kind of really completely orthogonal to what it is. What it is replacing metric spaces with combinatorial objects. It has nothing really intrinsically to do with dimensionality reduction. So I've just been displaying graphs. If you dig into the math, you'll find out there are actually simplicial complexes. So there are higher dimensional structures besides edges. That's not vital for anything I've said so far. So why do we do that? Well, the data is easier to manage. It's easier to search and query while maintaining the essential features of the data. Right? Those summaries contain the essential information that we want to learn. We can leverage known algorithms from graph theory, computational topology, computational geometry to understand in an automated way this output. So I've been displaying this to you with these nice visualizations, but it's not a visualization. All the information content of the summary is there before I put it on your screen, right? It's in the simplicial complex itself, and I never have to display it in order to utilize it. So this is more or less what it's about. So my analogy for compressed representation is cartography. Right? Cartography is all about compressing information. Right? There's this fable about this land where the cartographers make better and better maps. And eventually they make a map the size of the whole country, right? That's not a good map, right? The point is maps are useful when they're compressed representations, when they're summaries. Is it a road map? That's one summary. Is it a geologic map? That's another summary, right? Different summaries have different purposes. You don't want to go back out into the world and remeasure everything from scratch every time you have to do something. So, when we're making a map, we want to come to the problem with as few assumptions as possible, and we want to measure what's there. I don't know if this is a line or a circle. I'm going to measure it and find out. So I actually have a great story about that. So there's a paper that's going to be published in Science soon, or when it gets to the referee process, where this researcher, people have been using lines to measure how sick you are, right? They take all your symptoms, there's some regression line, and then they say, you're healthy or you're very sick, right? And they measure your state with this line. Well, he said, if you think about it, that implies that the experience of getting sick, you kind of just backtrack when you get healthy, right? But that's not how I experience getting sick, right? I start with a fever and I end up hungry when I'm healthy again, right? I didn't start right? I don't end with a fever again, right? Right? What am I saying? I'm saying you're healthy, you get sick, and then you loop back to get healthy. So people have assumed for a long time that you should be using regression lines. So what he did is he took samples of microarray data. So it's another biology example. I apologize for all the biology examples. We'll show some more other ones in a minute. And he just took this 1,500 dimensions, recording cellular activity, right? It's 1,500 dimensional space. He stuck it in our software, and he got these beautiful circles, right? So you think, I've never confused lines for circles, and yet there are whole industries built around confusing lines and circles, right? We're all subject to these biases, and we need to find tools, we need to use tools to help protect us from our assumptions. Okay, so that's what we do. We just want to measure what's there, what's in the data. And then we produce a summary, so we can solve our problem. Just like we produce road maps and geologic maps and housing price maps if you're in the Bay Area and you're looking for an apartment. Right? Different problems require different summaries. Different summaries come from different functions. So TDA is the machine that makes this all happen for us. Okay. So this here is more or less our motto: data has shape, and shape has meaning. Okay, so I'm probably out of time. Okay, I've been told I can keep going. So I'm just going to go through examples, real-world examples. So not synthetic examples, not PCA, not right. Real stuff. Real stuff. Okay, so First example, customer churn. These are contractual details for a major telco. So what I'm doing is I'm looking at what stage of the contract each person is in, and I'm building a different network for each stage. This is what I get. These are the people at the beginning of their contract. These are the people at the end. So what you notice immediately is that the summaries for each period are roughly speaking the same, right? That says that within each contractual stage, the total points I'm sampling from the space is the same space, right? I see the same shape. So it's not exactly the same, right? There's like, here there's like this, more of this like, I don't know, kissing phenomena, and then here they're a little bit more separate. But each one has, if you look carefully, has the same pieces in it. So the shapes are the same for all the different stages. Now I'm going to look at where the churn is. So, is this churn? This is not churn. Here's the churn. Okay, so at the beginning, what do I learn here immediately? At the beginning, right, the churn, all the people who leave are in very well-defined regions of the space. That says there are well-defined reasons for why they leave. And you can probably stop that from happening. As you get to the end, though, you see that the people leaving are kind of everywhere. They're leaving for lots of reasons. It's harder to nail down what's going on. But we see that immediately in this very complicated consumer space, what's happening with our churn. So, one other thing, actually, this second point, I'll mention that here, which is sort of fascinating. So, if I remember correctly, this data set is several million customers. But if you look at some of these small flares that appear in every data set, like down here, those over there, they have tens of customers in them. So we see this same group of tens of customers in a data set with millions of customers. So we get very fine resolution into the customer segmentation and customer behavior. Well, you might say, well, how do I know those are real? In this case, I would argue they're real because they appear in all of these, the same flare in the same spot. So even though it's 10 or 20 or 50 customers out of a million, or 3 million, I forget exactly how many, right? There's consistent behavior. On the other hand, some of these bigger blocks are 50, 100,000 customers, right? So we get a kind of multi-scale resolution segmentation of the customer space.
Okay, here's an example for industrial machinery. So this is a large piece of machinery, turbine, jet engine, locomotive, robot. I put all of those up there so you don't know which one it is. It has lots of sensors built into it, several hundred that measure, pressures, temperatures, rotations, forces, etc. And what you want to do is predict when it's going to break down, because unscheduled downtime is extremely expensive. So we took all the sensors and we z-scored them just so we could compare them to each other. Another way of saying that is that we got rid of the units on the sensors. There are other things you could have done besides z-scoring. I'm not saying that's God's gift to normalization, but it's the one we chose. So what we found, which actually surprised the customer, is that there were two signals for failure. So this here is a network formed by the output of a single sensor, and we got sort of the process to get into that single sensor. I'm not describing, it's a little bit long. But the thing that's surprising, and so how do I get a network here? That's another, so I'm using sliding window embeddings of that single sensor, so I actually have a network associated with the time series. In any case, the thing that surprised the customer is that there were two signals of failure. The one that was expected was this high mean, high variance. So that says this sensor is, several sigma above normal and is like being jerked around. They're like, yeah, that's going to lead to failure. The thing that they hadn't known to look for was the high mean, high low variance sensor. That's also a signal of failure. So in a single sensor, we found two different signals that predicted failure within 2 weeks.
I have a question.
Yes.
You mentioned here about sliding window being used on a data.
Yeah, there's a sliding.
Similarly, earlier you had that failure based on your lenses. You had sort of max or min, which I assume will be local minimum or local maximum. So,
That's right.
Yeah, so is there a way to find the scale? Because commonly that's an issue, like how much should be your scale, over what size of the data radius you should find the min or max?
That's right. Yeah. So
anyway, this technique, or we still have that problem?
So you still have that problem. I will say that, so I tried varying the window length over an order of magnitude and I got the same result. So I don't have a good explanation for why that is. Yeah. So it's robust under that choice in this example, but we haven't solved that particular problem, right? Right, yeah. So, yeah. Okay, here's fraud detection. This here is online transactions. So there's information about the account user, the device, how long they were on a certain web page, etc., about how they got to the shopping cart and then they checked out. And we know ground truth for fraud because we have chargeback information from credit cards. So this is fraud that's missed by their model because after the fact, the credit card owner said this is fraud. So these are the networks that we had, and unfortunately this is probably hard to see. There's this red area at the tip where the chargebacks are localized. Remember, generally speaking, we're looking for the kind of localization of some quantity that we're interested in. And what we did is we can, in the software, we have some statistical capabilities built in. We can examine what was going on there. And the important characteristic turned out to be the fifth item there, that the time spent on this page was significantly longer. So what that boils down to is that their fraud model had been built essentially for detecting for bots that are fast. And it had missed these far fewer cases of people who take a long time to sign out because they're using someone else's credit card information and address. So they're slow to type it into that page. And they were able to go back and fix that model. Okay, so I have a bunch of examples, but I want to leave some time for questions. So I guess I'll just end here. Thank you for having me. A plug at the end here, we are hiring across pretty much anything you can imagine. Data science, engineering, machine learning, sales, pretty much almost all positions. There's some people on the back from AYASDI. You can raise your hand if you're interested. Go talk to them or you can talk to me. And thank you for having me speak. Yeah.
I just had a question about your slide on compressive representation. Could you briefly describe how you construct this social complex and why it's sequential and not more general like CW complex?
So it's constructed as the nerve of a covering. Does that mean something to you? I think that's the answer to your question. Yeah. Yes? What's that? Yeah, they're available. Yeah, they can be posted. Yeah. Yes.
So there's a zoo of lenses you can use. What lenses have you found to be most useful in these first shots?
Yeah, so we don't solve the lens selection problem. at least not sort of, I just tell you what lenses to use. So the lenses you should use are the ones that are meaningful for your problem. So what does that mean? Well, everything here boils down to a kind of geometry problem or topology problem. So if you think through the question, the thing that you need to answer, you can come up with the right lens to answer it, right? But that's a hard thing to do. Generally speaking, we try things that seem reasonable, and we look for summaries that are useful. I don't have a great answer for you. Yes?
Can you explain more detail what you mean by using the x-axis as a lens?
So, to be a lens or a function to create a summary with respect to, it just needs to be a real valued function. What does that mean? It means to a data point, I give you a number. So using the x-axis as a lens means what number do I give to a data point? I give its x coordinate. So the x, right, that's a coordinate function, right? For every data point, I give you its x coordinate, that's a function. I can summarize with respect to that function. Yes, I think, yes. So I can't hear you at all. So there's a web page at Stanford. There's a research group called CompTop, Computational Topology. It's comptop.stanford.edu. And if you go there, you can find software and research papers. Yes?
So by using the topological data, you can find the outliers, like the example you gave us about this network coverage, and then you find them, you try digging into the data to find out what's the reason contributing to this.
I got I understood what you said up to we're finding outliers, and then what's the question?
You try to dig into the reason, to find the features, where then you have an outlier.
That's right. So first you look for the outliers, and then you find out why they're there. So that's sort of the reversal, right? The reversal of the process.
But the problem is that usually, like you said, we have like a very high dimensional, like thousands of dimensions. And then you find an outlier, you want to say like, okay, there's thousands of dimensions, so which one is the one that can become an outlier? Because in that case, I think fine, but in my practical working experience, deal with like thousands of dimensions, even dimension cross dimension, which can be even higher. So in that case, how can I tell which dimension will be most likely contribute to that specific output?
So I never, right, the output, so the dimension is about sort of the embedding dimension of the data. These are the coordinates I put on the data. The output doesn't have dimension attached to it at all. It's this combinatorial object. So I'm not looking for what dimension the outliers are contained in, right? I'm summarizing the shape of the data and looking for things, depending on what you mean by outliers, at the edge of the data, right? That's sort of a generic notion of outlierness, of things at the edge.
So basically what you mean is that try to first regard this, try to assume I have zero dimension and just plot the data, put them into different clusters to find the topological structure, and then from the point that we find there's an outlier to then dig into so from zero dimension to one dimension, whether this dimension will tell the difference between the major cases and the outlier cases. Is that what you mean?
I don't know. I don't understand your question, but we can talk afterwards in more detail about it. I'm just not quite following it. I'm having trouble hearing in here. Sorry. Any more questions?
Follow to that question. So is this technique more amenable to visualization rather than making quantitative interpretation? Not in a negative sense, visualization.
So-
what
So the question isn't, I would say, quantitative. So the question is, can I use this to make an automated decision? And the answer there is yes. Okay? But one way of thinking about this is that there's a world of algebra. And the world of algebra is a world of equations, right? But not everything is expressible in this world, right? Not everything is expressible as an equation. And we sort of leave that world and enter this sort of topology combinatorial world, which is sort of not algebraic. You can still make decisions in that world. We also have a way to rebuild models, sort of come back out of that world into the world of equations that I didn't get into at all. So you can use this information to build another model that looks more like a traditional model, but has digested the kind of the summaries here to make better decisions. And I haven't described at all how to do that for you, but I can tell you that it's possible. All right.